Hello students and welcome to another video lecture on logic design. We are in the process of studying combinational logic design and we have learned that a combinational logic circuit has outputs that are fully dependent on the inputs given to the circuit at the time. We have also seen that it is very easy to design any combinational circuit using three simple steps. Write a truth table, draw the K-maps and then draw the circuit in AOI or logic or universal logic. Digital computers perform a variety of information processing tasks, among which are arithmetic operations. One of the most basic arithmetic operation is subtraction. For example, take the subtraction of two binary digits. We can have 0 minus 0 equals to 0, 1 minus 0 equals to 1 and 1 minus 1 is equal to 0. These first three operations produce a difference whose length is equal to 1 bit. What about 0 minus 1? 0 minus 1 is equal to 1 with a borrow of 1. Now this fourth operation basically produces 2 bits as the output. One is called as the borrow bit and the other is called as the difference bit. Let us now go ahead and implement such a circuit. A combinational circuit which will subtract 2 bits is called as a half subtractor. Let us learn how to design it. The first step is to make a truth table. A truth table is made up of inputs and outputs. A half subtractor will have 2 bits as inputs. Let us name those 2 bits as A and B. Also, from the previous slide, you know that the outputs will be the difference bit, which we label as D, and the borrow bit, which we will label as lowercase b. When A and B are both 0, the difference is 0 and there is no borrow. When the inputs, however, are 0 and 1, then the difference is 1 and there is a borrow of 1. When the inputs are 1 and 0, the difference is 1 and there is no borrow. When the inputs are 1 and 1, the difference is 0 and there is no borrow. Let us proceed with step 2 of the design process, that is draw K-maps. Since we have 2 variables, we will require a 2-variable K-map and we will derive the expression for difference. So this is a 2-variable K-map. Plot the values where difference is equal to 1 on the K-map. So mapping those values on the K-map, we get it as this. Obviously, we cannot combine diagonal cells, so these remain as individual cells and we get the expression as difference is equal to A bar B plus A B bar, which is nothing but A XOR B. We also need to find an expression for borrow. So let us draw a 2-variable K-map for borrow and we plot the values where borrow is equal to 1 on the K-map. So mapping those values on the K-map, we get it as this. It is a single cell and we get the expression as borrow is equal to A bar B. We can now go ahead and draw the diagram as follows. A combinational circuit that will subtract 3 bits is called as a full subtractor. Let us learn how to design it. The first step of the design is to make a truth table. The truth table is made up of inputs and you have outputs. A full subtractor will have 3 bits as inputs. Let us name those 3 bits as A, B and C. And the outputs will obviously be difference and borrow. So when A, B, C are all 0, the difference is 0 and there is no borrow. Next we have 0 minus 1, which will give you a difference of 1 and a borrow of 1. Next we have 0 minus 1 minus 0, which will still give you a difference of 1 and a borrow of 1. Next we have 0 minus 1 minus 1. Which will give you a difference of 0 and a borrow of 1. You can continue this for all the other input combinations. In step 2, of the design process, we draw K-maps. Since you have 3 variables, you will require a 3 variable K-map. We need to find an expression for difference. So let us draw a 3 variable K-map for difference. We will plot the values where difference is equal to 1 on the K-map. So mapping the values on the K-map that we have here on this slide, we get, obviously we cannot combine these cells, so these remain as individual cells, and we get the expression as this. Now if we rearrange the terms slightly and remove some common terms, we get the equation as follows. You can still replace those equations with, this whole equation is of the form A XOR B XOR C. Also, we need to plot a K-map for borrow. For this also we will require a 3 variable K-map since you have 3 inputs. We will plot the values where borrow is equal to 1 on the K-map. So mapping the values on the K-map, we get it as this. Now instead of using K-map reducing techniques here, we will just write down the values of the individual cells as follows. We will remove a few common terms and simplify the equation until we get an equation for borrow as this. Using these equations, we can now draw a diagram for a full subtractor as follows. That's all for now. Connect to the classroom for further videos and learning material.